Welcome to Math with Professor V. In this video, we're going to learn about the ratio and the root tests. And these are two very powerful tests that can help us determine whether or not an infinite series is convergent or divergent. So first, we're going to focus on the ratio test, its statement, and work through several examples, and then we'll move on to the root test. So what the ratio test does basically is help us determine whether or not our series behaves like a geometric series. And this is done by looking at the limit as n approaches infinity of the absolute value of the ratio of two successive terms. So anytime you apply the ratio test, you're going to take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And then depending on what that limit comes out to, we have one of three outcomes right here. So first, if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n equals L, some number that is less than 1, then that tells us that the sum of an, or our series, is convergent. In fact, it's absolutely convergent, but that's a discussion for another time. If you want more info on absolute versus conditional convergence, I do have a video for you. I'll link it over here on the right and in the description, but let's just move on. Then, next outcome, if the limit as n approaches infinity of the absolute value of that ratio, a sub n plus 1 over a sub n, is some constant L that's greater than 1 or even infinity, then the ratio test tells us that the sum of an diverges. We have a divergent series on our hands. And then the last case is if that limit is exactly equal to 1. Then the ratio test gives us no information. It's inconclusive. Our series, it could be convergent, it could be divergent. So what do? You pick a different test. That means it was not an appropriate scenario in which to be applying the ratio test. Okay, so now let's work through some examples to see exactly how to apply it. So the question that we're going to be answering for all of the following examples is basically determine whether the series converges or diverges. First one, we have the sum n equals 1 to infinity of n over 5 to the n. I'm going to start off applying the ratio test, and I'll write it out just so you remember the statement. We're always looking at the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Now, n over 5 to the n, that is a sub n. So to find a sub n plus 1, I'm going to replace these n's with precisely n plus 1. You got it. So we have the limit n approaches infinity, absolute value, we're going to have n plus 1 over 5 to the n plus 1. So this right here is a sub n plus 1. And then I have to divide all of this by a sub n, which is the OG n over 5 to the n that we see up there. So over n over 5 to the n. Good? Okay. Now from here, if we're dividing by n over 5 to the n, that's the same as if we were to multiply by the reciprocal. So let me go ahead and do that. This is now the limit. N approaches infinity. And you know what, guys? Nothing's negative here. So I'm just going to drop the absolute value bars. N starts at 1. It goes to infinity. I don't need them. Okay? So we have now n plus 1 over 5 to the n plus 1 times 5 to the n over n. Good? Just some cute little parentheses. Now, when you get kind of slick at doing the ratio test, a lot of my students, they'll just jump straight to this step because when you've done enough of these, you see the pattern. But just take your time right now if you need to. Now we want to simplify so we can evaluate the limit. And the key comes from breaking up 5 to the n plus 1. I want to rewrite it or think of it as 5 to the n times 5 to the first. Because now, see how I have another 5 to the n on the other side? I can cancel both of those guys out. So now 5 to the n is gone. Let me rewrite what we have so far so you're not overwhelmed. So this is now the limit. N approaches infinity. I have n plus 1 over, there's just that 5 left, and n now. Okay? A couple ways you can evaluate the limit. You could divide everything by the highest power of n in the denominator, which is just n to the first. I don't know if your teacher just lets you do the pre-calc shortcut where you look at the ratio of the leading terms because we know the degree of the numerator and denominator is equal, so it's going to be 1/5. But assuming they don't, let me work it all out for you. So then this is going to be the limit as n approaches infinity. N divided by n, that's 1. Then we have 1 over n here, and then just 5 in the denominator. Good? Okay, so now we can evaluate the limit as n goes to infinity. 1 and 5 are constants, and then 1 over n, that's going to 0. So this limit is going to come out to be 1/5. And always remind yourself, okay, I just did the ratio test. What do I care about this limit L? I always want to compare it to 1. 1/5 is less than 1. So what does that tell me? That tells me that the sum, n equals 1 to infinity, of n over 5 to the n converges, absolutely, but we're just going to say converges by the ratio test. Now, obviously, we're doing ratio test or only root test for all of these, but just get in the habit of always writing out what test you use. It's kind of like citing your sources. Good? Let's try another one. Okay, example 2, we have the sum n equals 1 to infinity, -1 to the n minus 1 times 3 to the n over 2 to the n times n cubed. So starting off, just to save some time and space, I'm just going to jump to writing out the ratio of a sub n plus 1 over a sub n. Remember, this is a sub n. So first, for a sub n plus 1, I'm going to replace all of the n's with n plus 1. That gives me -1 to the n plus 1 minus 1 is just going to be to the n. Then this is going to be 3 to the n plus 1 over 2 to the n plus 1 times n plus 1 cubed. Good? This is just a sub n plus 1. Then I have to divide all of this by a sub n, which is just the original. So just relax, copy it back down. Okay, -1 to the n minus 1, 3 to the n over 2 to the n times n cubed. Beautiful. Now, anytime you're applying the ratio test and you've got this alternating portion, so when you have -1 to the n, -1 to the n minus 1, -1 to the n plus 1, that makes your series alternate, right? Well, when we take this absolute value, it makes all of these -1s positive ones. So then they play no role in the limit. So basically, you can dump them. I'm just not even going to write them anymore. They become positive ones raised to the n minus 1, but who needs them anymore? And then I'm going to multiply now by the reciprocal of the denominator so we can start cleaning things up. So we've got the limit, n goes to infinity. Again, I don't need absolute value anymore now that I've made all these -1s positive, so I'm just going to switch to parentheses. I'm going to have 3 to the n plus 1 over 2 to the n plus 1 times n plus 1 cubed times reciprocal of the denominator. So we're going to have 2 to the n times n cubed over 3 to the n. How are you guys doing? All right, great. Now this part will get repetitive. So once you start seeing patterns, you're going to apply it on a lot of the series that you use ratio test for. Again, I want to break down 3 to the n plus 1 so I can cancel it with this 3 to the n here. And think back, this is basically using our laws of exponents. This is the same as 3 to the n times 3 to the first. Similarly, boom, I can do the same thing here with 2 to the n plus 1. That's 2 to the n times 2 to the first. All right, and then you have yourself a little cancel party. You go, ooh, look at this canceling fun. 2 to the n, you are gone. Who else? 3 to the n, you are gone. All right, beautiful. I love it. I love it so much. Now we have the limit. N goes to infinity. From here, I just have a 3 that survived over 2 times n plus 1 cubed. Okay. Times, here's n cubed and nobody down there. N cubed over basically a 1. Okay, good. Now, if you want, you can take this 3/2 outside of the limit because it's just a constant. And then I'm going to focus on n cubed over n plus 1 cubed. So look, so this is going to be 3/2 times the limit. N approaches infinity. I have n cubed over n plus 1 cubed. Okay, you can group them together in the same set of parentheses if you like. Now to evaluate the limit, assuming we're not doing any shortcuts, I want to divide numerator and denominator by the highest power of n from the denominator, which is n to the third. So let me go ahead and do that. Divide by n cubed. Divide by n cubed. So now we have, keep that 3/2 times the limit as n approaches infinity. N cubed divided by n cubed, that's just 1. Now, n cubed, this quantity is cubed. So when I divide by n cubed, I'm just going to divide by n inside the parentheses. This is kind of like a slick shortcut to save you time from sitting there and actually multiplying this all out. So n cubed, when I divide by it inside something that's already cubed, I'm just going to divide by n to the first. So then this becomes 1 plus 1 over n, all cubed. Are you good? Okay. Then now we can evaluate the limit. So as n goes to infinity, those 1's are just constants. 1 over n goes to 0. Goodbye. So then this limit is 3/2 times 1, which is 3/2. And then you go, okay, I'm applying the ratio test. So what do I care about 3/2? I care that it's greater than 1. So what's my conclusion? That tells me that my sum, n equals 1 to infinity, -1 to the n minus 1 times 3 to the n over 2 to the n cubed diverges by the ratio test. Voila. Good? Okay, I got more for you. All right, just to spice things up, we're using the letter k. So we have the sum k equals 1 to infinity of 1 over k factorial. Now, if you haven't seen factorials before, I have a little basic video on it. I'll link it here for you and in the description. Check it out. But basically, if you have something like 7 factorial, that's the product of all successive integers down to 1. We stop at 1. Or something like 4 factorial. So you don't yell when you don't go 4. It's 4 times 3 times 2 times 1, etc. And then by definition, 0 factorial is 1. So something to notice when we're going to simplify expressions with factorial from the ratio test, you have to do this kind of slick maneuver very often. If you have n factorial, you could write that as n times n minus 1 factorial. Now, where did I get that from? Basically, I want you to observe here, 7 factorial. I could rewrite it as this 7 all by itself, and then 6, 5, 4, 3, 2, 1. That is 6 factorial. Another thing I could write is 7 times 6 times 5 factorial. So we're going to be doing stuff like this when we want to cancel and break down factorials, especially when we're applying the ratio test. Okay, you can cut this erasure that I'm going to do, okay? Okay, yeah. All right, so here we go. We're going to look at the limit, this time as k goes to infinity, absolute value. A sub k plus 1 would be 1 over k plus 1 factorial divided by original a sub k 1 over k factorial. Good? Now nothing's negative, so I don't need to keep the absolute value bars. And I'll go ahead, multiply by the reciprocal of the denominator. So now we have the limit. K approaches infinity. I'll have k factorial up top, and then k plus 1 factorial in the denominator. So we want to break up one of the factorials so we can cancel with the factorial on the other side in order to evaluate the limit. And you always want to break apart or break down the larger one. So in this case, k plus 1 is the larger one. I'm going to start expanding it until I hit what would cancel out in the numerator. And it doesn't take very long to get there, you'll see. So we have the limit as k approaches infinity of k factorial over k plus 1 factorial expanded is k plus 1 times k minus 1 times k minus 2, etc., aka k factorial. So you stop there. Then, yes, we can cancel. So k factorial goes bye-bye. And then now we just have the limit, k approaches infinity, of 1 over k plus 1. K goes to infinity, 1 over something getting very, very large, approaches 0. What do I care about this limit? We did the ratio test. Always remind yourself. And when I do ratio test, I compare this limit to 1. It's less than 1. So then that tells me that my sum, k equals 1 to infinity, 1 over k factorial, converges by the ratio test. Okay? I'd say anytime you run into a series that has a factorial, use the ratio test. Okay, example 4, we have the sum n equals 1 to infinity of n raised to the 100 times 100 to the n all over n factorial. Now, if they weren't telling me what test to use, as soon as I saw that n factorial, I'd go for ratio test without question. So here we've got limit, n goes to infinity, absolute value, a sub n plus 1, I'm going to replace all of the n's with n plus 1. So we've got n plus 1 to the 100 times 100 to the n plus 1 over n plus 1 factorial. You guys, do you feel ready to take a little shortcut? Do you feel ready, instead of writing over a sub n, to multiply by the reciprocal? I think we're there. Let's do it. Let's live on the edge. So times reciprocal, n factorial over n to the 100 times 100 to the n. Ooh, I love it. Okay, so now we got to break stuff up so we can have ourselves a little cancel party. So let's see. First thing I notice, 100 to the n plus 1. I can rewrite that as 100 to the n times 100 to the first. That way I can cancel with the 100 to the n down here. Love it, love it. Okay. And then with the factorials, notice here, we've got n plus 1 factorial in the denominator. Always break up the larger one. So I'm going to rewrite this as n plus 1 times n factorial, and boom, now n factorial is gone. There is something else we can cancel, but I don't want to stress you out just yet. So let's rewrite what we have going on so far. So now this is the limit. N goes to infinity. I don't need absolute value. Nobody's negative. I have n plus 1 to the 100. Okay, beautiful. N plus 1 to the 100. I have 100 to the first. Let me put that in the front. Looks cuter. Over just n plus 1. Maybe you're seeing what I could cancel. And then we have n to the 100 over here still. So 1 over n to the 100. Okay. Now here's kind of like the sneaky thing. If you got a little too excited, like I was a half a second ago, you might be thinking, oh, let me cancel this out with one of the n plus 1s. But then you're going to make it hard for yourself when you try to take the limit in a hot second. So what I'm going to tell you to do is let's have some restraint. I want to group these together because they're both raised to the 100. It'll be easier to evaluate the limit. And then I'm going to have 100 over n plus 1 separately. So watch, this is the limit. N goes to infinity. Keep these guys together, buddy, buddy. 100 over n plus 1. Okay. And then you see how both n plus 1 and n are raised to the 100. So then I can write that as n plus 1 over n, everybody to the 100. This is going to help us evaluate the limit because watch, we've got the limit now. N goes to infinity, 100 over n plus 1. If you want to break this up, you can write it as n over n, which is 1, plus 1 over n to the 100. And then now we're in business. As n goes to infinity, this is getting very, very large. 100 over something getting large goes to 0. So I have 0 times 1 over n is also going to 0. 1 plus 0 raised to the 100, that's 1. 0 times 1 is going to be the result. That's what my limit is, which is 0, which is less than 1. Always compare it to 1 when we do ratio test. So what does that tell me? That my series converges. Very good. Now you might say, oh, Professor V, I wouldn't have thought of that slick trick, right, to evaluate the limit. 1 second. And you know what? That's okay. That's why I'm showing it to you. And then you got to go practice on your own. That way, next time you see it, you'll remember, oh, that little slick trick where I put them together when they have the same exponent and I can easy peasy evaluate the limit. Okay, good. All right, example 5, we have the sum n equals 1 to infinity. In the numerator, we have the product of even integers, 2 times 4 times 6, all the way up to 2n over n factorial. As a note of caution, this numerator is not the same as 2n factorial. So 2n factorial would be different. That would be 2n times 2n minus 1 times 2n minus 2, etc., down to 1. So notice 2n factorial includes the product of even and odd integers. Here in this problem, they want exclusively even integers in the numerator. Now there is a notation of double factorial, which means only even integers or only odd integers if used appropriately. But most textbooks that we teach out of don't use that double factorial, so that's why they'll expand it out this way for you, okay? So how do you go about the ratio test? Please don't have a panic attack just because it looks a little weird. We're going to just go ahead, still apply the same definition we've been working with, okay? You don't have to invent anything new. So we do the limit as n approaches infinity, absolute value, a sub n plus 1. What I'm going to do is list out everything that I see here and then add in one more factor where I replace n with n plus 1. And then again, in the denominator, n factorial will be n plus 1 factorial. So watch. A sub n has all of this stuff, right? In the numerator, a sub n plus 1 would have one more factor where you replace n with n plus 1. And be careful, you got to put parentheses around there. In fact, this is so important. I'm going to put the watch out eyeballs so you don't forget. All right? And then this is all over n plus 1 factorial. Good? This is a sub n plus 1. So I've just added one more term, replaced n with n plus 1, and then n factorial becomes n plus 1 factorial. I'm going to divide this by the original, which is the same as multiplying by the reciprocal. So let's do it. N factorial over, just list everything out, okay? 2, 4, 6, up to 2n. How are we? Are we okay? All right, good. Now we have to clean up. I'm just going to rewrite everything so you can see, and we don't need absolute value. We can just switch to parentheses. I mean, who's negative? Not me. I'm feeling very positive right now. Okay, up to 2n. This is 2n plus 2. Okay. And then let's think ahead. I know I'm going to want to cancel these guys, so let me break up n plus 1 factorial into n plus 1 times n factorial. And then here, just rewrite n factorial over 2 times 4 times 6, all the way up to 2n. All right. This is going to be an epic cancel party. Can you see? All of this is gone. Bye-bye. So satisfying. And then n factorial is gone. You guys, we can cancel more too, but I just don't want to get ahead of myself. Here we go. Limit n goes to infinity. 2n plus 2. I can take a 2 out, right? And then what do I have left over in the denominator? Just n plus 1. Oh me, oh my. Yes, you can cancel again. So then the limit's 2. I don't even have to do anything fancy to evaluate it. And then you go, okay, I just did the ratio test. What do I care about 2? I always compare this limit to 1. It's greater than 1. So what does that tell me? I don't feel like rewriting it. This guy diverges by the ratio test. Okay. If you're on an exam, though, and your professor wants you to rewrite the original series, do it. It's not worth losing points over. Okay, I think we should have a good grasp of that. Now let's move on to the root test. As its name indicates, in this test, we're going to be looking at the nth root of the absolute value of an. So again, we'll be taking the limit, and here's the statement of the test. If the limit as n approaches infinity of the nth root of the absolute value of an is less than 1, then the sum of an converges. Converges absolutely, but we'll just talk about convergence. Second, if the limit as n approaches infinity of the nth root of the absolute value of an is something larger than 1 or infinity, then the sum of an diverges. And lastly, if the limit as n approaches infinity of the nth root of the absolute value of an is exactly equal to 1, then the root test is inconclusive. It gives us no information. Pick a different test. And don't pick the ratio test. So when one of those tests is inconclusive, the other one will be also. It's time to pick somebody else. Maybe limit comparison test, integral test, etc. And I do have a whole video on strategy for testing series. I'll link it also in the description because I know that's something that a lot of students struggle with, how to know when to use each test. But now let's just practice applying the root test. And then at the end of the video, we're going to compare when should you use ratio versus when should you use root. All right, first example, we have the sum n equals 1 to infinity of n squared plus 1 over 2n squared plus 1 all raised to the n. Now, a good indicator that I would want to apply the root test here is because I have all of this stuff raised to the n. Like, shouldn't we just take the nth root of it all? Yeah, we should. So we're going to look at the limit, n approaches infinity, nth root of the absolute value of a sub n. So no ratios here. You just take the nth root of the absolute value of the terms here. The limit n goes to infinity, nth root of absolute value of n squared plus 1 over 2n squared plus 1 all raised to the n. So when I take the nth root of something raised to the n, it cancels out. And then notice nothing's negative here. So I don't need to keep the absolute value bars. In fact, I was so excited I ditched half of them. So now all we have is the limit as n approaches infinity. This nth root is gone. And then absolute value bars, I don't need them. I just have n squared plus 1 over 2n squared plus 1. Good? Okay. Dividing by the highest power of n in the denominator in order to evaluate the limit means we'll divide everybody by n squared. And then let's see what we've got. This is going to be the limit as n approaches infinity. In the numerator, we'll have 1 plus 1 over n squared. And then in the denominator, 2 plus 1 over n squared. As n gets very, very large, 1 over n squared, that'll approach 0. And then I'm just left with 1 over 2, so my limit's 1/2. What do I care about 1/2? I just did the root test. I always compare this limit to 1. So 1/2 is less than 1. So then this tells me that the sum, n equals 1 to infinity, n squared plus 1 over 2n squared plus 1 to the n converges by the root test. Good, let's move on. Okay, second example, we have the sum n equals 2 to infinity of negative 1 to the n minus 1 over natural log of n raised to the n. Pay attention, it's important that the sum starts at 2. If it started at 1, we'd have problems because natural log of 1 is 0. So it's intentional that it starts at 2. All right, we're going to apply the root test. So we're going to look at the limit as n approaches infinity of the nth root of the absolute value of negative 1 to the n minus 1 over natural log of n raised to the n. Okay, when I take the absolute value of negative 1 to the n minus 1, it makes it positive 1. And I don't even need to write it anymore. So just replace the whole numerator with 1. Now, I'm taking the nth root of all of this. The nth root of 1 is just going to be 1. The nth root of natural log of n raised to the n is going to cancel out that exponent. So in the next step now, I just have simply the limit as n approaches infinity of 1 over natural log of n. I'll explain that again. This is all positive 1. Nth root of positive 1 stays 1. Nth root of natural log of n to the n, natural log of n. That's it. So now n goes to infinity, natural log of n, hopefully you remember the graph. So as n gets really, really large, natural log of n also gets really, really large. This all goes to 0. So that's my limit. And then we just applied the root test. So I always compare this limit to 1. It's less than 1. And then that tells me, all right, my sum n equals 2 to infinity, negative 1 to the n minus 1 over natural log of n to the n converges by the root test. Good. All right, example 3, we have the sum n equals 2 to infinity of n over natural log of n raised to the n. So let's apply the root test. Limit as n approaches infinity of the nth root of the absolute value of n over natural log of n, all raised to the n. So everything in here is already positive. No need to worry. We're starting from 2 to infinity, so you don't need the absolute value bars. And then when I take the nth root of this quantity raised to the n, they cancel out. So now we just have the limit as n approaches infinity of n over the natural log of n. Now, as n approaches infinity, that means the numerator is approaching infinity, and natural log of n is also approaching infinity. So we have an indeterminate form of the type infinity over infinity. Now, don't get too excited. We can't apply L'Hopital's rule just yet, because remember, we're only allowed to use it when we have a differentiable function in the numerator and denominator. And the terms of a series are most definitely not differentiable. So what do you do in this scenario? Well, you just say, I'm going to come along and define a function, f of x, that is exactly what we're trying to find the limit of. You're just replacing n's with x's now. So f of x is going to be x over natural log of x. And it might seem silly, but you need to appreciate on a deeper level, it really shows that you have an understanding of what L'Hopital's rule implies and entails. So you just got to do it, okay? Now we're going to look at the limit as x approaches infinity of x over natural log of x. Remember, you can only use L'Hopital's rule when you have indeterminate form of the type infinity over infinity or 0 over 0. So make sure you have that first, which we did. And then now we're going to go ahead, apply L'Hopital's rule, differentiate the numerator and denominator separately. So derivative of the numerator is 1. Derivative of ln of x is 1 over x. So then now we have the limit as x approaches infinity of just x, which is infinity. So now I can go back and say, all right, since the limit of f of x was infinity as x approaches infinity, then that means that the limit as n approaches infinity of n over the natural log of n is infinity also. That comes from here. And what do I care about this limit? I care that it's greater than 1. So then this tells me the sum, n equals 2 to infinity of n over the natural log of n raised to the n diverges by the root test. Okay. So between the two, if I had a favorite, it's the ratio test for sure. But the root test in these scenarios, when you have a bunch of stuff raised to the n, it works really nicely. Okay, now let's look at some examples and decide which test is appropriate. Okay, I'm not going to tell you which test to use. We have the sum n equals 1 to infinity of 5 times n factorial squared over 2n factorial. What do you think is appropriate? As soon as you see factorial, it is ratio test time. That is right. And no panic attacks because you have n factorial squared. Okay, just remind yourself, what does it mean when you have something squared? You have it times itself. So I'm just going to literally write out n factorial twice, if that helps, okay? So here we go. Let's apply the ratio test. Let's look at the limit as n approaches infinity of the absolute value of a sub n plus 1. So I'm going to go through, replace all of the n's with n plus 1. And then notice, because I have this factorial squared, I'm going to write it like this. N plus 1 factorial times n plus 1 factorial. Do you feel better already? Good, because I do. Yeah. All right. Over, here's what could be a dangerous moment, but you're going to make sure it's not. 2n factorial. You have to put the quantity n plus 1 in parentheses. That is crucial. We need more watch out eyeballs. Oh no, don't miss that. That will completely change your result. Okay, this is a sub n plus 1. I'm going to divide this by the original a sub n. So I'm just going to jump to multiplying by the reciprocal. So we have 2n factorial over here, and then 5 n factorial squared. Let's just write it out twice. N factorial, n factorial. Good? Okay. Quick glance, nothing's negative. I don't need to keep those absolute value bars. And then let me start breaking down the larger factorials. Okay, so we've got here, this is the limit as n approaches infinity, 5 times. N plus 1 factorial is n plus 1 times n factorial. I've got another one, so another n plus 1 times n factorial. Are you okay? Wonderful. Now, 2n plus 1 factorial. When you distribute that 2, it's 2n plus 2 factorial. Yes? Okay. We have 2n plus 2 factorial here, 2n factorial up top. I want those to cancel. I want to cancel somebody. You always break down the larger one. In this case, 2n plus 2 factorial. So 2n plus 2 factorial is 2n plus 2 times one integer smaller would be 2n plus 1. I got to keep going because I still can't cancel just yet. Now I have 2n factorial. Good? And then everybody else over here stays the same. 2n factorial, 5 times n factorial, n factorial. Okay, it's cancel party time. See, did we have a cancel party with the root test? No. That's why this one's more fun. This one's more fun. Okay, first and foremost, 5. Get out of here. 2n factorials are gone. And then literally a 2n factorial. Anybody else? There is, but let me rewrite it and then we'll get there. Okay, so this is limit n approaches infinity. What do we have up top? N plus 1 quantity squared. And then down here, we just have 2n plus 2 and 2n plus 1. Let me take the 2 out of here. And then I have n plus 1 and then 2n plus 1. Good? Okay, yeah, more canceling fun. N plus 1 from the denominator goes bye-bye with one of the n plus 1s up top. So then now I have limit n approaches infinity, n plus 1 over, yeah, we might as well. We can just distribute. What's that going to be? 4n plus 2. Okay. Divide everybody by the highest power of n in the denominator. So we're going to divide everybody by n to the first. You do it in your head though, right? It's just going to be 1/4. So this is the limit. N approaches infinity. 1 plus 1 over n over 4 plus 2 over n. So what can I say? This guy goes to 0. This guy goes to 0. And my limit is 1 over 4. What do I care about 1 over 4? I care that it's less than 1. So then I can say this series converges by the ratio test. Good? All right. All right. Next one, we have the sum n equals 1 to infinity of n over n raised to the 1 over n plus 10, all raised to the n. So when trying to decide, I'm thinking to myself, is it going to be manageable to write out a sub n plus 1 and simplify it when I divide by a sub n? And what's kind of deterring me from that is this 1 over n exponent with the n as the base. I mean, it's going to get kind of nasty if we try to do ratio test. And since all of this is raised to the n, I'm thinking root test might just be a little cleaner. And that's the way to go. So here we go. Let's look at the limit as n approaches infinity of the nth root of the absolute value of n over n to the 1 over n plus 10 raised to the n. Now, all of this is already positive. I don't need to worry about keeping the absolute value bars. So this is just going to be the limit now as n approaches infinity. And then be careful. So the denominator is raised to the n. That will just cancel out when I take the nth root. So I just have n raised to the 1 over n plus 10. But in the numerator, I'm going to have the nth root of n, which is the same as n raised to the 1 over n. Okay? Good. Now from here, this really differentiates a student who is on it versus one who can be a little bit careless. N raised to the 1 over n as n approaches infinity. Do you know where that's going? So the base n is approaching infinity. The exponent 1 over n is approaching 0. And infinity raised to the 0 is an indeterminate form. It may be 1, but it also may not be 1 at times. So how do we evaluate this indeterminate form? Using L'Hopital's rule, and we have to introduce a natural log in order to move the exponent. Now, if you're rusty on this because you haven't even thought about doing that since Calc 1, you're not alone and you're just in luck because I recorded a new video on L'Hopital's rule. So I'll link that in the description in here. But let's just work through it off to the side. So we're going to go ahead and let y equal, remember we need a differentiable function. So we got to switch from n's to x's. Y is going to equal x to the 1 over x. Okay? And what I want to do is consider the natural log of y. What's that ugly natural log? Hold on, let me get it together. Consider the natural log of y, which is the natural log of x to the 1 over x. Why do we do this? That way we can move the exponent down front, and then I have 1 over x times the natural log of x. So now I'm going to take the limit as x goes to infinity of the natural log of y, which is the limit as x goes to infinity of natural log of x over x. Now I can apply L'Hopital's rule because the numerator is approaching infinity. The denominator is also approaching infinity. So here we go. Tell the people we're doing L'Hopital's rule. And then now we have the limit as x approaches infinity. Derivative of ln of x is 1 over x. And then derivative of x is 1. So what's this limit approaching? 0. Good. But remember, originally I was interested in the limit as x approaches infinity of just x to the 1 over x. This is the limit of the natural log of x to the 1 over x. So how do I undo that natural log? I have to take e and raise it to this result. So this tells me the limit as x approaches infinity of x to the 1 over x is going to be equal to e raised to whatever I just got, which in this case is 1. Okay? So we can conclude that this limit in this particular case does equal 1 from all of this. That means the limit as n approaches infinity of n to the 1 over n is 1. And then now I can come back and finish evaluating this limit. So n to the 1 over n, that goes to 1. This also goes to 1. And then at long last, what's this limit going to be? Well, I have 1 over 1 plus 10. That's 1 over 11. And what do I care about the fact that my limit is 1 over 11? Simply that it's less than 1. So since this limit's less than 1, this series converges by the root test. Okay? And if you're like, Professor V, this was too fast, too furious, I didn't remember all of that stuff, then go back and watch the video on L'Hopital's rule because we just got to move on and look at another series now. All right, last one. We have the sum n equals 1 to infinity of n to the 5th times e to the negative n. Don't let the negative exponent freak you out. If it helps, just remind yourself an is n to the 5th over e to the n. Okay? So do you want to do ratio test? Do you want to do root test? You actually could do either. My preference, ratio test. I'll do it that way, and then I'll show you what you would run into if you did the root test and why maybe you don't want to. So we're going to look at the limit as n approaches infinity of the absolute value of a sub n plus 1. So that would be n plus 1 to the 5th over e to the n plus 1 divided by a sub n. So I'm just going to multiply by the reciprocal, e to the n over n to the fifth. Good. Okay, now nobody is negative, so I don't need to keep writing absolute value. And then let me clean things up. So we have the limit n goes to infinity. You know what I want to do? We've done this before, so now's your time to shine and go, oh, I remember that little slick trick when we were doing the limit. And both of these are raised to the fifth power. So let's put them in the same set of parentheses to the fifth. Oh yeah, n plus 1 over n to the fifth. And then I have times e to the n over, how should we rewrite this? So good, e to the n times e to the first. Boom. So e to the n cancels. Let's clean this up. I'll write it as n over n plus 1 over n. You know what I mean? So this is going to be the limit. N goes to infinity. This is going to be 1 plus 1 over n to the fifth times, this is just 1 over e. Beautiful. N goes to infinity. 1 over n is going to approach 0. So this is just 1 plus 0 to the fifth. That's 1. So this limit's going to be 1 times 1 over e, which is 1 over e. E is about 2.7, so 1 over e is less than 1. So then I know that this series converges by the ratio test. Okay. Now, I did say you could use the root test if you wanted, but let me show you why it's less clean of a solution technique, okay? So if you were to take, I'll still do this one so you can see, the limit as n approaches infinity of the nth root, I don't need absolute value, nothing's negative, so just for things to be clean, nth root of an, you'd have n to the fifth over e to the n, right? And it might seem tempting because you're like, I got e to the n down there, why don't I use the root test? Okay, then you have the limit as n approaches infinity, just e in the denominator, but here in the numerator, n to the fifth, and then when you take the nth root, you're going to have n to the 5 over n. Why is this not desirable? Because again, as n approaches infinity, this is an indeterminate form. It's infinity raised to the 0, and you're going to have to do that same process that I showed you in the previous example, where we took the natural log, redefined a function of x, that way we can use L'Hopital's rule, etc., etc. It's doable. You'll see the end of the problem, and sometimes that's the only way to solve something, right? But in this case, I'd rather avoid all of that and just do ratio test and cut to the chase. You know what I mean? Okay, so that concludes the video. I hope it was helpful, so please give it a thumbs up, subscribe if you haven't already, tell your classmates, your friends, whoever you think would benefit from this video or from my channel about it. And if you need more examples, ratio test, root test, I will link more examples, more videos that I've done in the description. I also have a full playlist of videos on sequences and series, and it'll definitely help you because this is one of the most challenging units for students in Calculus 2. Also, I've got lectures on Calc 1, Pre-Calc, Calc 3, linear algebra, differential equations, so much stuff. Everything's organized into playlists, so take some time, browse my channel. It'll be your new favorite resource to help you through your math classes. And then you can also follow me on Instagram, TikTok, Math with Professor V. Comment down below which was your favorite problem that we did in this video today. And any requests that you have for more topics from sequences and series or in your calculus classes, leave them down below too. I'll be back sooner than later. Bye guys, love you.